thank you very much for having me here. And I'm going to be shaking it up a bit right now because we've had now 2 talks about QKD, about all the cool things that you can do with that either terrestrially or in space. But I want to go now look towards the future, and maybe perhaps even why the future is already a little bit here in next generation quantum networks that we are building also in at QTech. But before I do that, I think I would like to invite you back to 1969. I guess in any of the quantum networks talks that you've been in through the years, you might have seen this picture where Leonard Kleinrock at UCLA made a first successful but kind of unsuccessful connection to his colleagues at the Stanford Research Institute. And I had to look this up. I had no idea what the history of the internet was way back when. But then I came across this picture. And I would like to ask you, how many of you think that it took longer than 10 years to go from that first network to go to this fully US spanning network?
Yeah.
Longer than 10 years. Okay. I feel like you're all being extremely optimistic, which I think is really good if you're in this field. And the cool thing is you're actually correct, because it only took 8 years to go from that small network to here. But to put that into perspective is that my PhD has been about 4 years, and we're still working on a quantum network. Yet it took only 8 years to go to a fully intercontinental spanning network. And you see those wiggly lines; those are satellites. So already that happened as well. But why is that so much harder? Why is it so much harder to make quantum networks? Well, if you would allow me to take you to like what the landscape looks right now of quantum computing. We have all these different islands of different quantum computers, either from the same vendors or from different vendors, but they all operate in their own bubble. And so, pick any of your favorite vendor and put it here. But what pictorially I would very much like to do, obviously, is that not only would I like to have these islands, but I would like to have these islands connected. Because we have learned very well from the past, 40 years, that actually connecting computers together brings together a new information age, right? The only reason that I was able to find pictures when I said arbitrary quantum computer was through the internet. And therefore, I very much believe that connecting quantum computers at a large scale will bring a similar type of transformation to quantum computing as the internet did for the computer. I'm going to go into why I think that. Let's see what version we have here. Yeah, let me quickly, I'll get back to this in a second. I would like to first highlight a little bit about what these networks look like, and sort of from a schematic point of view, and then we go deeper down into the details. So you can think of it as if I would now, on an arbitrary distance, and this can be tens, hundreds, thousands of kilometers if you wish, there are probably going to be several hubs of different quantum computers that work very close together, not unlike data centers right now. But then I would like hubs to be connected together, and I would like to be able to do that quickly, and therefore I would like to use photonic links for that, and hopefully even already deployed fiber network infrastructure, because we work really hard to already get that in the ground. We don't want anything else. But when I say that I want to connect quantum computers together, what I actually mean is that I need different quantum computers to be entangled together, or individual qubits to be entangled. So we're not just now talking anymore about having entangled photon pairs be somewhere. No, I'm talking about being able to have a quantum computer send out a photon that's entangled with a qubit that's already there, send it over somewhere, do a measurement where another photon from another computer comes, and therefore do a entanglement swapping such that I can have 2 solid-state computers be entangled together. And effectively, that kind of looks like this, because if I want to go over a network, obviously, I would now have to make entanglement between any of these points in a very fast manner. And one of the key things that will help me do that is sort of the building block of a quantum repeater, or a quantum memory even, that allows you to store entanglement for a little bit while you're making entanglement across this full link, and then measurements across this link will herald an entanglement again between these two different quantum computers. Cool. I think we're on the same page. This is a hard task, but I do want to highlight, and unfortunately I have to quickly step back, namely to, going to the ideal of being able to entangle qubits together in different quantum computers. Along this way, we're finding very useful other purposes. We've already had, of course, the great talks on the QKD systems that are now being implemented. And I would like to call those in the category mostly of point-to-point qubit transmission, where your QKD allows for sharing of keys, but you still have to trust some of your measurement devices. And then you can go one step further. That's the talk of Ingrid right after me from our friends at Qbert that do a measurement device independent QKD. So then you go one level higher in what your usability from qubit transmission can do, where you have sort of more native multi-point to multi-point qubit transmission. But this is still, of course, on photons only. And then we can go one step further, and this is where I operate. This is the world of entangling qubits and having different quantum computers be entangled. And over the last decades, there have been really great work done in this field on an algorithm level, what you can do with entangled quantum computers. And one really great thing that's been also developed at universities here in France has been algorithms on blind quantum computing in the cloud. Meaning that I have my own quantum computer, I can let a cloud computer perform a very difficult calculation for me without it knowing what it's doing. And I think that's one of the really holy grail sort of privacy computing. You can even verify, that's like an addition to this, is a little bit more overhead in your algorithm, but you can even verify with these algorithms that the cloud quantum computer did in fact not learn anything from the thing that you're doing. Now, and this is the future that I want to work towards, and that's of course then the quantum computing fully integrated in a quantum internet, where you then allow for distributed quantum computing to happen, or cluster quantum computing, not very much unlike the current internet, can also be put together. Or say you want to combine different types of quantum computers together that all have their own benefits, right? I have maybe one that's really good at processing really quickly, or ones that have a very long memory, but I all want them to exploit the benefits from each other. Okay. How do we get there? Because this sounds amazing to me. One of the key challenges in order to do that is obviously that we're working really hard on the hardware level, but there's still no sort of standardized layers in software that allow us to have full stack quantum network management. And there have been some really great proposals on, especially on, in this case, you see on the right, on the link layer systems that are software defined, where in the end, I just need to be able to sit behind a computer and say, I want to perform this calculation and not have to think about where are the quantum computers, how do I let them be entangled at the right time? This can be a very complex routing. And so we need to redefine all these layers that already exist for the current internet on how do I transmit a qubit, how does it have to be routed over, how does entanglement generation have to be routed over a network? Then also still, you have to have a layer that tells a physical computer or a physical part, a quantum computer, go make entanglement now between these and these points. And then you still have a stack within a stack, which is the physical layer of a quantum computing system that then still that has to execute actually the generation of entanglement making, which also needs a lot of qubit operations in between. So this is a very dense stack, and I would even say, you're doing both quantum computing and networking kind of at the same time, which is very hard. But really great work is being done also by the Quantum Internet Alliance to sort of consolidate this and come up with a standard that works for everyone. But then I also would like I said, I want to have deployed systems that operate on current fiber network infrastructures. And as it turns out, it's not a given that a quantum computer that is able to even send out photons sends it out at a telecom wavelength. Actually, most qubit platforms go in the visible wavelength range and not in a low-loss telecom range. So we also need to do something there. And then, of course, the other big challenges are, okay, then I still need inter-system compatibility because I promised we would need to be able to connect different vendors together. And in the end, I also want entanglement generation rates that are, well, let's say usable, right? I am not asking about sort of mega entanglement generations per second, maybe already, but that would be a good goal to end up. For the last 10 minutes, I would like to take you a little bit on what I've done on the first 3, because there is already a lot of work that we're trying to combine most of these things in hardware. But first, I would like to show you a bit of what right now the state of the art is in the field, so that we can place this a little bit better in this space. We've had really great work done on quantum memories, both in Munich at ICFO. There's also company Connect, and of course, I think more that do quantum memory related things. And those networks span sort of 400 to a kilometer range, where you can have either teleportation of a qubit state between memories, or simply have showing entanglement between different qubits over long distance. Quantum dots are also there, although they, because of their coherence, lack sort of the ability to go really far distance. And then in the center is where I work at, and that is the usage of color vacancy centers in diamond, and for example, even the nitrogen vacancy center. That's been a workhorse for the last 10 years to operate both as a small quantum computer. It has a spin on its own. There are other spins around that even can work as a quantum register. Where 2 things have been done. First, in 2015, we also did a loophole-free Bell test. That was the first loophole-free Bell test using solid-state quantum emitters. So that I feel like very much hooks into what we've heard this morning from Alain Aspect. And then most recently, in the last 2 years, there was the first multi-node network built that connected 3 different NV centers together that were on different chips. And this was still within a lab, right? This was confined, but there was a entangled state between all these 3 nodes. Okay, all these things are, I feel like, really great steps, but none of these have ever really went outside of the lab. And so that's where I come in, because we put ourselves a goal. We said, no, we want to recreate parts of this. We want a quantum network that spans different cities, and have them be entangled together, but also be fully independently and remotely operated. So no cheating, nothing in the lab combined. The only thing that will be connected between these 2 are fibers. And that's really hard. That's also why it hasn't been done yet, until, well, hopefully now. So this is the goal. We want long-distance entanglement with these NV centers. Mostly because we know them really well, and they sort of build on all this knowledge of the last 10 years. So that was very helpful for us. And we're employing quantum frequency conversion to go from this natural wavelength of the NV center, which is not in telecom, to go to telecom, such that we're also compatible. We actually convert down to the telecom L band. And this is what it looks like. It's already there. This is me and my PhD colleague, and we've been working for the last 4 years on a full system, as you can see here. On the left, the node 1, on the right, node 2, and in the center is our measurement station. And we've kept it in the lab for a while, but don't let the wires fool you. In the end, actually, the only things that really are connected between these nodes are fibers. Actually, only 2 fibers. And we've kept them here because we, of course, wanted to make sure that a system like this that has never been built before, where we can independently operate them and also remotely, works in the lab before we take it out of the lab. And we were able to get some verifications going of that. I'll show you that in a second. But most importantly is that we really focused on building a scalable hardware platform. So not only does it have standardized control, but anything you want also includes automatic calibrations, automatic control of our control electronics, such that in the end, the communication qubit is simply a modular building block in this whole thing. And so you kind of can see that, of course, in the end, we're doing network experiments, but we're actually also controlling a quantum computer at the same time. But this has been extremely helpful for us to be able to do these long distance or attempts at long distance experiments. Yes, and only actually the cool thing is that with these automated checks and automated controls, we only have about a 30% overhead in other things that is not entanglement generation. And this is what I wanted to show you earlier, is that we've been trying this system out in the lab, and this was last year, where we've shown that we have these interference of indistinguishable photons from these two separate nodes in the telecom band, and both NV centers, both qubits, were detuned from each other, which means that they're not natively compatible on a wave on interference-wise. And so what we can do with our quantum frequency conversion is that we can actually use that system not only to convert the telecom, but also have it be the tuning knob of actually tuning them together. So we sort of have this building block towards inter-system compatibility. We have a tuning range where we can all get to a same target. And the most recent result, and that's been actually really in the last months, is that we've had successful entanglement generation between these two systems in the lab with about 0.1 hertz entanglement generation rate, including the overhead that we have in automated calibrations, as what I shown you before. Yeah, and now actually, as we speak right now, we're packing up. We are packing up one of the nodes to be sent, well, in this case, 10 kilometers line of sight away, where we're gonna rebuild it in a very fast manner. We already took this into account, of course, from the start of this project. We're gonna rebuild it and rerun these entanglement experiments, because we have already proved that we can do this in the lab. It works remotely, independently, it all works. And actually, the only thing that's harder, well, maybe not harder even, is that the length of fiber between them increases. But for us, that's not really an issue anymore. Okay. To wrap up, I do want to say, we still have some other open standing challenges in the field of connecting different quantum computers together. We can provide part of the inter-system compatibility, but of course to a limited degree, because you would still need to generate photons out of these systems, and some other systems are not compatible with photons natively, and so you would need some transduction technologies to make that happen. The NV center for us is limiting in the entanglement generation rate that we're able to achieve. It simply is not sort of built for being able to send out a lot of light all the time, and so there are these new type of quantum devices that are mainly other color centers or enhanced color centers in cavities that allow for much higher photon emission rates that simply, actually to a large degree, are somewhat plug and play in a modular system like this, right? In this case, 90% of the work that I've been doing is sort of engineering anything else besides the quantum device, even though we're using it heavily. And now if you would have a different quantum device that operates even better, would be, of course, very wise to plug that in and use that in this system like this. And of course, what you saw is that this is a big system. It was still, a full lab, and you could see it to scale with me, right? Sort of 2 meters high and quite big. And we're really confident that we can also miniaturize a lot of these things. We've been working 4 years to a prototype where design freeze basically now can be made, because we know that this works really well. And so packing this up into something that is either smaller in rack form, and of course, that's part of what my research group is, and also working on, of course, to have something that's even more integrated into photonic structures, also in diamond, actually. And I want to leave you with this, because my goal is to continue all this work. I really believe that technology like this can enable this next wave of transformation of quantum computing. And so I really would like to continue building a full stack hardware deployable quantum internet in the coming years, and share its progress with you all here. Now, of course, I did none of this by myself. We have a really huge team over time that both from QTech in the group of Ronald Hansen, supported also by Quantum Delta NL together with TNO. It's been a very long trip. but we've made it work really well. And one thing I always have to highlight is that we actually have also a quantum network simulator running right now on online, and this is the Quantum Network Explorer, that allows you just to tinker basically with what quantum networks look like. What does it mean if you want to teleport a state from one place to another? It's all very, very interesting. And I'd like to take any questions right now, right after the talk, or at the community drinks of Quantum Delta NL later today. Thank you.